Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Uh, I welcome all of you back to our first stream of the live season, the fall season. We had a bit of a summer hiatus, and as a result, we are getting started again. As many of you know, just to get things started here, just a reminder, Atlanta Functional Programming is mission is to promote and talk about functional programming in various languages, Lisp, Haskell, C Sharp, what have you. Those of you who are interested in giving a talk to in our meetup, please let me know, and we'll get you scheduled. Um, right now, the um, we're right now looking for speakers, and we're currently going to be virtual until in the near future, um, until we start hearing back from other venues regarding COVID restrictions being lifted and so forth in the Atlanta area. So, folks who are interested in the in-person meetups, please stay tuned in our meetup page for announcements regarding that, and hopefully we'll let you know about what's going on there. Those who want to give a talk and are not in the Atlanta area, by all means, also give a shout out. I'm Bugram on Functional Programming Slack. I'm also Bugram in the Lisp Discord server. You can contact me in either location and let me know that you want to give a talk, and we'll get you guys scheduled. Today we're going to be continuing our discussion of the an exploration of the cells library. I know it's been a while since we've actually touched and created a introduction into the cells library. Please don't worry. Today's agenda includes a brief overview and review of what we covered last time, as well as continuing our exploration. Without further ado, I guess I will get started here. Just give me just 1 second. Um, All right. So last time, as I mentioned, the cells library is a library dedicated for doing what's called Dataflow-oriented programming. As many of you know, this is kind of along the lines of libraries that are written in a reactive style manner, right? So what that means is you're looking at libraries that essentially create like an infinite stream of data, and their purposes is there is some sort of input event, if you will, or stream of input event that'll trigger a cascade of additional events to occur. It is through a implementation of, in many ways, a model that behind the scenes creates a set of implicit observers between cells or slots of a given common Lisp object instance, and those observers essentially get triggered whenever particular cells change. Okay. The inspiration of the library, as you recall from last time when we discussed this, is spreadsheet programming. The idea being that in spreadsheets, you end up, writing these huge, data tables with cells, and some of those cells can change, and some of those are formulas actually that get updated whenever their input cells, the cells that they depend on, get changed accordingly. Great. We went through a couple of examples of this, and I'll very quickly go through them. One of them is your very simple example, which is a cell that takes in an input, and what happens is and these are cells that essentially can be changed within the runtime once the object instance is created. And then there are two types of cells technically in the cells library. One is input cells, which you can manipulate, and the other one are called ruled cells. And there are three different types of ruled cells that we covered last time. Ruled cells, lazy ruled cells, both of which is lazy evaluated versus eager evaluation. And there were also, as well as in lazy ruled cells, cells that can only be triggered once, and it will never be reevaluated after dependencies or dependent cells change. In the second case, they have something called until asked, which is the ruled cell essentially is holding off evaluating the expression that it once a change event occurs until the next time it is read by application code. And of course, always asked, which is cells that are always never evaluated until read. And what that means is they are always lazy. So what happens is a change event that happens, but whenever change events happen, until the change event is actually triggering a read on the lazy ruled cell, it's not going to actually be evaluated. The expression in the model is not going to actually be evaluated. And we've seen a couple of these examples, and we'll just quickly go through them. One in this first example is an example of a simple cell model that contains one input cell, and one ruled cell that's eagerly evaluated. And what that means is every time a change event happens, so whenever cell 1 occurs, since cell 2 depends on cell 1, what it's going to do is this change event will automatically trigger the evaluation of this expression here. In this case, we're basically doubling the value of whatever is in cell 1. And you can see here we also defined that, if you're going to have these input cells, a lot of times you're going to see models where they have accessors provided to them, and they're used to read and write what's in the cell. Now, that said, some folks might be thinking that there might be cases where we're only going to do write only. This framework gives you the ability to go ahead and do write only cells that are inputs. It's entirely up to you in the designer, because these are essentially extensions. The actual cell classes are meta classes that are written on top of the common Lisp object system. So they're leveraging the meta object protocol to actually go in and create these. Def model itself is actually nothing more, as we recall from last time, just a macro that expands to essentially defining a def class, as well as the methods associated with the different cells in that def class. And you can see here, as we encountered last time, that the cell itself, the model, the def model cell, is a subclass from the actual subclass from the cell's model object. We also encountered a couple things here very quickly. We said that we could create ruled cells that are depending upon each other. In this particular example, if you recall from last time, our input cell essentially triggers not one but two different change events because of the fact that cell 1's changes will invoke the expression and evaluation of cell 2, which will subsequently evoke the expression and evaluation of cell 3 once the evaluation gets updated. And this is something that you can see being very useful when you're building up complex models that leverages many different types of expressions and formulas in determining when a particular change event happens, what should occur in different parts of the system. This is commonly something that could be used in, and I think I mentioned this last time too, in like particular cases like UI applications where change events in the UI not only require background changes to some sort of lower level model, it can also be used to encounter and provide information for um, inserting stuff into a database or even informing the user through some UI representation, of what's actually been triggered. Forgive me for the trains in the background. I will try and if you guys can hear that. So, lazy cells that we quickly, and this is just very quickly, we went through once asked here, and once asked is the one that I mentioned is the lazy ruled cell will only occur, the evaluation can only occur when the the change event is actually explicitly demanded by the application code. So if you we created an instance of this here, let's say we have some sort of cell that is an instance of our simple lazy cell. Oops. And let me actually increase this size to give you guys a little bit more of a font size here. And we evaluate this. If we ask for, cell 1 of the once asked cell, you will see that, it's still 1, but internally, cell 2 has not yet evaluated yet. Okay, it means it hasn't been instantiated yet, even in this make instance case. Here, if we call this, if we actually call the reader, this will trigger the calculation. So you may have noticed that there's a small pause between the access and the return, and that's because behind the scenes it is actually going ahead and evaluating the expression, then returning its results, then going ahead and returning whether or not the computation succeeded or not. And we can see this. Unfortunately, there's a lot of things about this because cells have been around for a while. There's a lot of things that I wish it had, but it doesn't. And one of them is in some of their public API, for example, if you try to describe this, you will know that there's macro, whether or not they're macros or functions, but there isn't a lot of interactive documentation built into this. So we're just going to kind of go through this as we go along. If we're trying to do this in the until ask case, and there was an issue last time when we tried the until ask case, I think it was because of the fact that I may have did something incorrectly in terms of picking the correct the correct until evaluation. But we could try a couple of things here. I thought my understanding was. Hello, did okay. So let's try this guy right here, and let's go ahead and evaluate that. And it's an undefined variable self, right? And that's because of the fact that this guy more than likely evaluates as something that doesn't include self. It includes self, but it's not actually retrieving what's there. Okay, hold on a second. Let me do this. Okay. So let me try and see if I could do. Let me see if I can do this. Shoot. Okay. There we go. One second. Put a couple of these applications that I have running in the background. Okay. Well, and this going and okay. So now that as well. Okay. So now let's see here. So we do cells, C condition. And what I'm doing here is a little bit of a dirty hack, but this should work. And it looks like it is giving you a warning that this may not occur because it's being called with an odd number of arguments. Let me see what is it's complaining about. Alright, so it looks like the reason it's complaining is because what's happening is the ruled cell is essentially being called the ruled cell is being called with which converts into kind of a make C dependent cell. This is a call to construct the actual dependent cell and hook it up into the larger level model. Since one is eager, the other one is actually not. It is actually complaining that I'm trying to essentially construct a rule and pass it into another rule, which doesn't make any sense. So this unfortunately cannot work the way I expected it to. So this solution is probably a buggy solution. All right, looks like I can't show until asked a little bit more until later, but we'll move on. So until asked is one of those cases where it would be nice to be able to use this, but once asked actually can handle a lot of cases that until asked uh, uh, will will handle. It's a little bit more stringent of what occurs. Um, so you can once asked you could think of is initial initial observation evaluation, okay, but change events until asked, I'm not going to. I mean, until asked, I won't make those changes. And until asked is make everything completely lazy um, until it's actually requested. At which point it'll become unlazy. It'll eagerly evaluate the code and then return it. Now, there's a couple of things that that I did not show in these models that I'm just going to quickly mention here from last time. I thought I'd clear this up. Although these are def models, okay, you don't have to have slots that are actually cell types, okay, whether or not they are input cells or ruled cells or what have you, okay. You could simply have a model that has normal slots, okay, because again, what happens is these def models. This def model is nothing more than a macro that converts into a def class behind the scenes. Now I know that's kind of I'm kind of opening up the box a little bit, to kind of get you to think that, oh, this is just nothing more than a def class. But please believe me, it's only, and you just need to understand that at the end of the day, the machinery that these objects are being created, these def models, are nothing more than standard common Lisp objects that you can use normal def methods to override and hook into the rest of your common Lisp system, okay, your common Lisp application, okay? And that is very powerful because that means you could define these interactive models where necessary, and you could just simply hook up the appropriate callbacks without having to worry about any sort of like glue wrapper code that needs to be needed to deal with serialization and deserialization of objects from one paradigm to another paradigm. You don't need to write those adapter classes in a lot of cases because the adapters are just a result of the fact that we're using common Lisp objects. Now, there might be cases where adapters are necessary just merely because of some communication between the libraries, but in general, because these are just common Lisp objects and the rest of the system's common Lisp objects, you can actually just go ahead and override whatever existing methods that are available in your application if you need a particular def model to actually interact with some other API, provide an override from some other interface that was defined in your application framework. So to illustrate this, I'm just going to quickly create an example here. Simple no cell example. And what this is going to do is it's going to have technically, let's say, shoot. Okay. So it's going to have a cell that is going to still be technically an input cell for now, but it's going to also have, in addition to that, we're going to call this accessor, cell 1. It's going to also have a cell 2 that instead of being a ruled cell, like we had before, we're going to go ahead and make this guy just be nothing more than be a constant, okay? And we're going to have a reader here. and call this cell 2. Okay, and we're going to have a cell 3 here that is essentially our ruled cell, and I'm going to be using eager cells for the time being for this, just to make things a little easier on us. And what this will do is, let me just do this. Just do just comment this guy. Let's code reload later. Okay. Well, what this will do is nothing more than it will take our cell 1 and multiply it by our constant. So this is just going to create nothing more than multiples of 5, okay? And store it into our cell 3, okay? This is our model, okay? We're gonna go ahead and do this. Oops, sorry, not cell in, C in. Okay, compilation successful. Let's go ahead and create an example of this here. And what this is going to do is let's go ahead and do let our instance, let's call it object make instance of simple easy. Sorry, no cell example. And what this is going to do is we're just going to go loop for I from 1 to 5, 10, do, and what we're going to do is we're going to do just a quick set f on. Actually, why am I using the loop in this case then? Sometimes I wonder why I complicate things. We can actually do this being, we're just going to do times I10. Okay, set f, cell 1, of our object I. Then what we'll do is we're going to do a format. We're going to show you the value of cell 1, cell 2, and cell 3. Just to show you what this is going to do. Okay? And we have cell 1, okay, cell 2, and cell. Okay. So now we go to here, we'll see the results. Okay? And notice the single cell has never changed. Okay? This is we can have these kinds of constants, okay? And they don't have to be constants. You can totally make this into an accessor. But the point is that the machinery, all right, will never change, okay? What does that mean? That means that if a change event occurs, cell 2 will never get reevaluated, okay? It's just a normal slot, okay? Let's see how if this is true, okay? Let me go ahead and do this. Let's make this into an accessor so we can actually go and change it. And let's make the initial argument 0 for the time being, okay? So we're now changing this a little bit. Now, one thing to note is let's go ahead now. We go through and we will, for the time being, do our normal printout. And then what we're going to do is we're just going to go ahead and change cell 3 to 3, okay? Sorry, obj to 3. And what we'll do is now show you the same code here after 3 is changed, okay? Now, if this is correct, what's going to happen is cell 1 will not be changed. Cell 3 will not be changed. But cell 2 will say 3, okay? So let's see that. I may have done something wrong here. Cell 2. Okay. Let's see here. Is the no is not of type cell. Okay. So let me go ahead and do this. May not like the fact that I'm trying to do a init form. Init. Where is okay. That's okay. That's okay. Is not of type cell. Okay. It may be the fact that I'm attempting to make a change and it's accidentally triggering an issue with the rest of the model. So let's see. If I do that, let's see what happens. Yeah, that's the problem. It is thinking that this is still hooked into this cell. So even though it's not actually the first time I evaluated, it looks like what's happening is it's treated like a cell, all right, which allows us to go and change here. But by doing this here, we're registering it as being a cell inadvertently. And the only reason why it worked before is we never actually modified it. So if we do this, what that means is basically this, for having constants, is okay, right? And we can actually go ahead and see that this is, wait a second. I'm going to have to restart. Restart. So, let's restart my Lisp here. Okay. And let me also load. Okay. Okay. As you can see here, if we just go ahead and reevaluate it, we're going to still get this. And it's because of the fact that this is registered as a constant cell, essentially. It's no cell. It's not registered to anything. But if you, since we're using it in a ruled cell, if you attempt to make a change in this, the expectation by the cell machinery is the fact that this cell is going to cause a change event. Okay, just merely because of its use here. All right. So that, I just learned something there. So let's try not using this here. Let's go ahead and make this 5 for the time being. Okay. And let's do this. Compile this. All this is fine. Now, let's go ahead and try and set. Sorry, I have to go in here. And let's try and set cell 2 to 3. Now, if we do anything with the other two, you'll see nothing's going to happen. These two will get evaluated immediately. These prints here. There's no change that's going to occur behind the scenes. And you can see that in cannot be, oh, sorry. I accidentally made that into a reader instead of an accessor. Let me do that again. 1 second. Okay, so now we got this, and if we attempt to change it, you will see, what now, hills, cells, cell. What is it triggering on? Cell 2, slot value, no cell example. Interesting. So I may have to go in order to get this working. I may have to actually, let me see if there was. Right. In order for me to do this, I have to do this. I forgot. I have to provide this. The reason why we need to, we're going through this exercise is because there's a couple things regarding interacting with the rest of the cell engine that needs to be registered, and the reason why this is occurring is because, as you can see, it wasn't registered as a normal. It's not being informed. The cell engine is not being informed that this particular cell is just a normal cloth slot, and to ignore it. Instead, what it's doing behind the scenes is assuming the default to being some sort of cell, just because I didn't provide the fact that this is T. And we talked about this last time, the fact, and I forgot about it, my apologies, that cells, essentially, by default, the slots are going to be true. Okay, what that means is the cell engine is going to manage that slot. It's not going to be managed outside. And that means it's going to enable it to have particular characteristics. So if you don't provide it, even if you don't use like cell cin or any of the ruled cell macros, it's going to still be treated like a normal cell. So if you go and try and do a set F on it, you've essentially changed its type behind the scenes, which is causing the cells engine to go haywire. So here, now actually, this would then work based on this. Because now, go ahead and do that. If I do this, we should have no. Weird. Let's see. CWI C stop. I think it messed up the triggers when I did this. Why would this cause an issue? Interesting. Okay, I may have to reboot. The cells engine looks like it got messed up again because of my mistaken thing. Okay, so let me just go ahead and do this because we saw this earlier. Let me go and do slide, restart, Lisp. And let me go ahead and reload. Okay, and you can see right here already what's going on. I'm going to go ahead and change this guy to our cell anyway. Notice that although I changed it to a 3, when cell 1 is 9, it should be 27, but instead it's still, treating it as the original init form. And that's because although we have a editable cell inside of it, it is a normal, because we provided, and this is the key thing here, we provided this saying that cell is nil. We're basically telling the cells engine, hey, this is a class slot. I'm in control of it. I don't want you to treat it as any sort of spreadsheet cell. It's not going to create any sort of change event for you. It's not going to change anything in terms of triggering events that's going to be used by the rest of the model. So just go ahead and keep it as is and you'll be okay. All right. This is particularly useful, especially when you want to add, say, a metadata field that you want to separately leverage for, say, creating models that have some sort of administration tasks. Okay, and when you are instantiating them, for example, you could certainly use that bookkeeping elsewhere. So this way, the changes in the bookkeeping doesn't necessarily trigger all sorts of events behind the scenes. Now, you may certainly want to do that, and for complex models that might be necessary, but for your normal bookkeeping that you want to keep track of, an example of this is maybe not having to deal with change events whenever you write something to like a log file. Okay, this is a very common thing that some folks might have. So you might have a internal slot representing the log that you're writing to, and you don't want that to trigger any sort of change events because you're always going to append to the log. You may not do anything else. Now, yes, it's very true that you could certainly make it a cell, a cin, an input cell saying that this is a log that I'm always going to be changing, but that's kind of useless unless you're wanting to take action on that log elsewhere in your program. So make sure you know about where you necessarily need to use your no cell examples, your ephemeral cells that are necessary whenever you are, modeling particular event streams and so forth, just because that becomes a design decision when you're building up applications using cells. Okay. We ended last week with, our last episode with essentially an introduction to and debugging of families. Okay. So to briefly get you guys up to speed again on families, a family is nothing more than you can think of families as being essentially related cells that are connected to each other kind of in a tree-like structure, okay? And if you recall our last talk about families, we were dealing with this example that we got from the Stefano documentation on cells GTK. It was actually introducing cells altogether as a tutorial. All right, we're building up this node example. Okay, a family, as I mentioned last time, is essentially going to be an object whose types are organized in such a way that there's a tree of model instances called your children from your parents. They don't necessarily they're not model classes, so they're not being instantiated. You're instantiating them ahead of time and you're going to reference them inside your family, and you're going to use those family methods in the API. A couple of them we're going to see in this example again, like FM other and FM self, I think, and kids, to actually go and reference each of the individual nodes inside your family. And you can use something called the value accessor to actually go and have a top level sort of running value that's essentially a reduction of your children's values all accumulated together into some sort of top level node that you can then access by simply calling out value. Now, the example that we went through is let's say that you're trying to create a calculator expression. Okay, a simple example. This is a common thing when you're trying to build a calculator program. You might have different types of arithmetic expressions. Right now we're using addition for the time being, but it could certainly be any sort of expression that a user types in. Okay, you could certainly make that into an interactive family instance of nodes that you could then call val on the node to actually go and determine the value of the node. Okay, and one thing to note about this family is the fact that we ended up having this issue where you're trying to build the kids in this family, and it unfortunately was giving this error saying that the cell itself is undefined. Okay, undefined variable, and we ended it here for debugging purposes. As it turns out, it's because of what the kids represent. Okay, the kids behind the scenes, okay, is a macro that essentially assigns to self and uses that to actually create the structure that's going to be leveraged later on to access different children inside of the hierarchy when you ask for it. Okay, but they all need to be hooked up to this top level parent, and right now this top level parent isn't actually necessarily defined. It's only being globally set to whatever the dis pointer is pointing to. But if you look at this, there's no dis being passed into this variable. Why is that? Well, the reason is kids and families require you to actually be created on top of a rule. Okay, the rule is when the instance is created, then go ahead and hook these guys up into this hierarchy. So what we need to do to fix this is we actually need to go ahead and wrap this into a ruled cell. Oops, I'm sorry. Okay. Okay. Cells. And by doing this, now we have a cell that should be good. Just make sure by clearing out our history here to make sure that this isn't actually causing any issues. No warnings. So we're good. So now when we call this map op family function, what's going to do is it's going to first construct this top level node, this make node, and the value itself of this node is a rule that's going to essentially reduce the addition. It's going to take all the values of every child in this tree and grab its value, and then it's going to go ahead and reduce it, and then its initial state is going to be this value. Okay, so the initial state of the root now is going to be this particular addition, right? So what is the initial state of this? Well, we've just created essentially a tree representing, you could think of this like an AST, where the operator node is addition at the root level. The left child is an input cell 5, and the right child is another sub-expression, which includes the operator node, which is determined here by a ruled cell. Again, you're seeing this rule being an application of multiplication on the children. And then we have in these two children 7 and 9. So obviously 7 times 9 is 63, plus 5 is 68. That's where the 68 comes from. Okay, and then obviously here, when we change any of the nodes, we have, we're going to get a change event, and the change event is actually going to cause all these rules to, percolate up and provide you with the value 95, because 10 times, and we change it to 10 times 9, and then now 10 times 9 is 90 to go to plus 5 is 95. What is each of these things going to doing is kind of what we ended with last time. We're going to touch base on it today. The first thing, again, we're going to have to start with the def model, all right? When you're defining the model and you're planning on building a family on this model, you're going to have to subclass from family, okay? Every model that's going to be a family needs to be subclass from family. This gives access to those FM functions that we were looking at earlier. All right. The FM functions again is a query API on top of your family. All right. The next thing is when we're instantiating it, your values are all going to necessarily be ruled cells. Okay. They're not, the leaves of the family can be input cells, but the values at the top level may not be input cells. They may end up becoming, in a lot of cases, ruled cells, okay? Ruled cells, in this case, I'm using eagerly evaluated ruled cells. You could certainly set up cells that are lazily ruled cells, but that are once asked. I did not set that up here in this case. So we could certainly, for example, change this guy to be C1s, and this is going to be giving you the same results as before, because once we asked it, it's going to be, it's not going to evaluate it again. All right, that's the difference here. If you see, when we change this to once asked, the change of the 10 doesn't necessarily activate a new change event to propagate up here. Okay, and that's particularly important to be aware of. Okay, so for now, more than likely, you're going to end up just dealing with eagerly evaluated rule cells. Okay, so now if we do that here, we get back to what we had before. The next thing to know about is this: what are these the kids guys? Okay, what the kids does is it creates a flattened list of the tree structure, okay, to make it easier to actually go in and figure out what leaves are available inside of the tree. Okay, this is a very useful thing, particularly when you're trying to create complex models with multiple layers of trees, subtrees that need to have many children, but you want to really ask, who are my children? All right, who are my input cells? That's where this particular thing comes into play. And this now allows you to then, again, as I said before, this flattened list requires you to make actual children, which you do with the MakeKid API. And the MakeKid API requires, if you want to reference a particular child, and we use that later on, especially when we're querying the family, you would end up labeling it with an MD name. So in this case, our node here, if we wanted to access specifically N5, we could certainly just use :N5 passed in as a property to MD name, and it will label that node N5 for later retrieval. And then MakeKid is essentially nothing more than a wrapper around MakeInstance ultimately, so it will take the REST init args, and it will then allow you to take the init args of the class that you're interacting with, which in this case is node, and allow you to construct instances of it. So this val comes from, again, the actual def model, but the MD init arg is coming, MD name init arg is coming from MakeKid. MakeKid is using that as an argument for labeling that particular node prior to calling MakeInstance. So we're building this, and we've created 2 layers of children here. As you can see, a child doesn't necessarily need to be just a single input cell. We can actually make itself a ruled cell that has children of itself. So here in this tree, you have 1 child and 2 children and 2 grandchildren, technically. The 2 children at the first level is a input cell and an operator, a ruled cell, and the 2 grandchildren are these 2 input cells, 7 and 9. Okay, so that's how you read this this API. Once this is defined, now you can actually you can actually utilize it. So when this is constructed, all this in construction is going to propagate and provide an initial state where the ruled cells are all evaluated, and that's where you get the 68. Okay, when val is called on the root. Okay, but how do we access and change a particular cell? Well, we label these cells inside the family. Okay, there's an API called fmother that is querying the actual family. All right, what it does is it allows you to provide a member name, okay, and provide a starting point. Okay, if we look at this here in the root, the key values that you're seeing here, you have to pay attention to it. The starting value, if you don't specify it here, is cell self. This is a very important thing to take note of. Okay, if you are accessing fmother, if you're using fmother to query a family outside a ruled cell, you have to change the starting keyword argument. okay, to specify which subtree you're actually dealing with, okay? This is a very important thing to be aware of. And if if you wanted to, if you knew right now here, this is doing a top level. Since we have root, this is doing a top level query. But there's another way of actually querying, but I have to go and look this up again because there's other functions. If we look at this, if you look at this, fm collect, these are all flattened functions. Collect if, collect sum, descendant, descendant if, descendant sum. You can actually go and query all these APIs here. Gather, there's a couple of gatherings, heritage here, includes, and so forth. And we'll touch base on these kid things in just a minute. Additionally, you can call maps and all this kind of stuff. But if we go and look at the other ones, you have some of these particular querying things that querying APIs. Honestly, the one that I think you would be using a lot is FM other, maybe the immutable version of it. There is also this one, which is I haven't figured out what exactly this particular FM other and some of these other ones are doing in terms of the predicates, especially. Just mainly because of the fact that I haven't had a chance in real code. I ended up just using FM other in a lot of cases. But these are all the different ways of you being able to essentially provide a subtree of the tree that you're actually referencing, and then you can actually go in and prune the number of nodes you actually have to search through to actually get what you want. For now, though, we're going to just continue here. Okay. After this, like I said, we have to start. We have to override the starting keyword argument. So we're going to just go ahead and say, well, since root itself is a node, start at root. Root is obviously a subclass of a node family, so it's going to go ahead and query down and just do a simple string comparison, as you can tell by the test results. And we can do this. All right, and this doesn't necessarily have to occur here. We could certainly, bring this down here. We could change this to being any query argument. So this is just providing a name, right? So if we go ahead and change this, obviously this is going to change our next execution because now it's 63 plus 10 instead of 90 plus 5. And you can play around with a couple of those too as well. I mentioned that cells is built on top of the observer pattern a lot. It's an implicit observer, okay? Dataflow programming itself is just based on the observer pattern, okay? And I know I bring up observers and I talk about it here a bit when we were talking about cells, but it's very it's something that you should not take for granted, because not only can you define models that have these input and ruled cells, you can also define observers. Okay, this is Cell's way of essentially creating def methods that are interactive, that are hooking into the Cells engine. Okay, we will define an observer today. Observers are just nothing more than a function, okay, that will execute whenever a change event occurs, okay, specifically whenever an input cell is modified, okay. So to define this, we're going to have to call we're going to have to define the slot that we want to observe on, and then we're going to have to write a couple of overrides. Okay, so let's go back to simple cell. Okay, we're going to write a observer on simple cell just because it's a little easier to handle this one, just because it's a two slot cell that it's two slot model that we've defined here. All right, so to example observer, go ahead and we're going to go ahead and start with obviously our code here. We need to provide the slot name, and then there's a couple things that are going to be there. There's a couple of optional arguments: the old value, the new value, and so forth. The slot name that we're going to be looking on is cell 1. What is self in this case? Okay, so the first optional argument that you need to provide is what is self? Okay, so in this case, our self is going to be a simple cell. Think of this, this is a macro, okay, so I'll show you what the macro expansion looks like. And then we'll get new value, old value, and then old value bound p. It's a predicate that allows you to essentially check to see if the old value is actually bounded or not. Okay, and when we load this, you can see here that behind the scenes, it's creating this thing called cell slot value observe. Okay, and again, it's using, for folks who are forgetting our def method syntax here, just a brief review. Def method, slot name, what method combination are we using? Okay, in this case, standard method combination is usually compositionally. Here we're just doing prog-n, which means it's going to run in sequence, one after the other. Okay, and we're restricting it on the simple cell instances. Okay, because we have a couple of cell types that have the same cell, but as many of you know, even though they're using the same name, the def generic is usually the same, and the different specializations occur in def methods generated later on when you define def models. So now we can actually go in and develop the function body for this guy. I'm just going to be making this a very simple function body. I'm going to just say if old value bound p, actually I don't think I need to specify this, new bound p, that's your predicate. Actually, you know what? We do not need to specify that. I don't think I need to do that. I can actually not specify any of these other ones because they're not arguments. They're not necessarily needed, but we'll do this anyway. All right, new value is a old value a. We're just going to go and look at the changes that are being done. So we're just logging to the console every time something changes. All right. And then we'll do new value of value. Okay. Let's see if this works. Let's create an instance of our simple cell. You can see that the old value was nil. And the simple cell new value is 1 because obviously when you first initialize it, it's going to change it. Let's go ahead and do this. Also, old value bound p, just to see what's passed in. All right. All right. Right. Sorry. Let's do this down. Old value bound p. Okay. There we go. Okay. Now, if we go ahead and change, I don't recommend you do it this way, but I sometimes do this for when I'm playing around in the REPL. Try to name the variables. Let's say that we put 3. You can see that we can actually check to see that the value is bounded, and we can totally see the old and new values. This is particularly important for a couple of cases. One, mainly because of the fact that in certain use cases, these types of observers allows you to add additional functionality that may be required for, say, auditing purposes. Okay, like let's say that you're building a data collection system, right? And you want to know when a person logged in what changes he made to a particular form. Well, you don't want that logging logic necessarily in the form itself, okay? But you certainly want to keep track of it, okay? So whenever they make changes to those particular values that aren't being computed, because again, ruled cells are computed properties. Think about this in terms of data modeling. You have your computed properties, and you have properties that are fixed properties that are provided by the user or some sort of data source. So in this case, you want to be able to say, okay, when this guy is coming in and building up this data collection system or what have you, he made these changes to these particular form entries, okay? And you could certainly add those, make sure that the form is tied behind a cells model, and then you could use these observers to actually augment what's currently being done in the model to provide, to just add the functionality. And everything is nice and clean in terms of actually reading the system, the stuff that matters to the actual overall application, is separated from the cross-cutting concerns, like logging these values into, say, potentially a database that holds that information. I'm going to stop here for a second and see if there are any questions. I'm going to look at the YouTube, see if there are any questions coming out on YouTube. No. All right. Excellent. Perfect. I hope this is going to be useful for you folks. I had a fun time going through some of these things, so this is particularly useful. Okay. So let's see here now. Okay. Let's start with now this one thing that I have not shown you yet, which is let's say that we changed this value to 3, but we wanted, this is why I should have actually done this. Let me go ahead and create here quickly example make instance simple self. Okay. Oops, sorry. I am total butterfingers today. Okay. Sometimes I wonder. Okay. This piece slurp. Nope, not create that. Okay, did not work. My apologies, folks. For some reason, my key bindings aren't working. So let me just quickly create this. Let's go ahead and do cell 1 and example 3. Okay, so we now know that we have this example where we're setting the value to 3. If you try to set the same value again, you're going to notice that it did not actually trigger the observer event. That's because change propagation, change events actually validate and verify that a true change actually occurred. So this way, it's not occurring every time. It's there's no need to propagate it because it's already been accounted for. It didn't actually change. Okay, but if they are different, it's going to go ahead and trigger this particular model, which I thought was particularly cool. Okay, so let's talk a little bit about unchanged. Let's see here. Let's try, yeah, unchanged if. So there's this property that on cells that you can provide that allows a predicate to be provided to the cell, so that if it is true, a change propagation event does not need to be thrown. Okay, just like what we saw before when they are equal. Okay, the way this is kind of added is, honestly, you can add it here. It is a property on the cell itself, and you can provide the a lambda function or some sort of predicate. So in this case, I'm just going to go ahead and say, do not propagate if x is less than 5. Okay, so 1 through 4, no chain event is going to occur. All right, but once you hit 5 and above, you're going to start seeing change events and you're going to see the observers actually being created. All right, so let's go ahead and do that. Let's go reset our example. Oops, not this example. Oops, go down here. Yeah, this one. Okay, so you see the first time it created, obviously because it's constructed, you're going to see a change event. But let's say that we try to do cell 1 example 2, and let's see, invalid number of arguments 2. Oh, got it. This is on the actual unchanged if thing. Okay. Let's do. We're going to ignore. Let's say. Let's do it particularly interesting. Let's say unless the differences, which is, I'm going to use the absolute value here of the difference of x and y, okay, is less than 5, do not call the change event. Okay, so our initial value is 1, so that means 0, 1, 2, 3, 4, okay. Anything above that, once you get to, actually, I will put this as 1. So this way, it's going to, let's do 2 to illustrate this. 5 is fine. We'll do that. Okay. So what this is doing is obviously it's going to take the two values, check the old and new values. If the old and new values are greater than are 5 apart or more, a change event is going to occur. If they're closer to each other, it's just going to ignore that change event. Okay, so we're going to go ahead and create this. Let's set 2. 2 happens. If you see cell 2 of example though, it did not get changed. Let's try 3 again. Okay, because we tried 3. Did it change? No, it did not change. So that unchanged if is actually going to be suppressing those change events, but it'll allow you to go ahead and change the input cell anyway. So to really drive this home, I'm going to go ahead and just trigger. Let's do this. Let obj be an instance of our simple cell, and we're going to go ahead and do this 8 times, and we're going to go ahead and set cell 1 of our thing to x. Okay. Really, I should use I because I is always your standard variable. Okay. So the first time the object is going to get constructed, we're going to get an observer event. Okay. Again, we've talked about this. It's constructing. It's going to obviously create this change event. But until we hit 6, you will not see a change event. After 6, it's going to go ahead and create. So for 6, 7, and 8, you're going to see a change event. Let's see this. Illustrate. Interesting. For some reason, it still did not trigger. Oh, right. It's going to be 6, and it's not going to be it's not going to trigger again because 7 and 8, the difference between x and y is going to be less than. It's always going to be it's always going to be going against the old value that's currently been set. So it's going to be 7 minus 6, and then 8 minus 6, and so forth. So we saw when it got constructed that a change event occurred. We saw that the predicate got triggered another change event when it was exactly 5 away. All right. This is particularly neat if you wanted to suppress certain changes from occurring. One thing to note, and this is one thing I'm not entirely sure, so I may as well go ahead and print this guy out. What is old? And I hope x, the first argument, is old, and the new value is the second argument, but I cannot say that for sure for this change event. So let's see. So you're going to see more logging information being passed on here. Let me just go ahead and clear my REPL history so we can actually see this in isolation. So old, so it's flipped around. The first argument is the new value, and the second argument is the old value. So this new old. Okay. Let me just go ahead and do that, and do this, and do this. All right. Are there questions? I hear a mic in the background.
Sorry, I was just scratching my head.
Okay, not a problem. Let me know since you welcome, Carl. Let me know if you have any questions.
I can't see your slime buffer.
Oh, okay. Let me. My apologies. Let me. Completely forgot. This is.
close my eyes to visualize it, and then I fall asleep.
Yeah. 1 second. We can rectify this. Once slime. For some reason, let me just share my entire screen here. Okay. Give me 1 second. May have to refresh the Hangouts call. Okay, let me share the screen. And let's see what happens. Okay. For some reason, Hangouts is giving me trouble to share my screen in my desktop. So my suggestion is if you go to our YouTube live stream, you'll be able to see the notes. I think in the meetup, the top level meetup page for Atlanta Functional Programming, we actually have the link, but I can just go ahead and paste it here as well, just so that you don't have to go hunt it down. I have it open here.
I just hunted down the AFP on GitHub.
Yes. Let me go ahead and where is it? It is oh, right. Why am I in, let's see here. Go to the channel. Okay. This is the channel. Okay. If you click on that should allow you to get to the stream.
Part 2 cells, part 2, there's 2 of them. Well, there's a live now. Okay, I see what's going on. I'll click on that one.
Yeah, my apologies. For some reason, the YouTube channel customization keeps on pasting it twice, and I haven't figured out why.
Okay, now I'm with you.
Okay. So, and let me know if you have any questions. I'm going to post my GitHub my code to the AFP repository after this. So folks who are interested in actually looking at the code and seeing how I butchered some stuff and provide some feedback, it'll be great. Let me know. But hopefully it'll also be a good consolidation, because there were several resources of things that I've been using to actually go in and figure out how some of this works. Because again, like I said, some of the documentation was a bit outdated when I started looking into this, and so as a result, it ended up becoming a little bit of a pain. Okay. Let's go back to lazy cells for a minute, because I just found another way of actually dealing with lazy cells, which is kind of useful. Which, as usual, it's always great to find different ways of doing this when you look at different documentation things. Once asked, until asked, and always can actually be passed into a lazy cell if you provide and it's really like 2 ways of like dealing with it. Okay, you can provide this when you are constructing the cell itself, or you can use it when you're building the ruled cell using the macros that I showed you earlier. All right, the C once, I think C question mark once, C question mark and until, and I think there was another one too as well that that is available for you. But I'm going to try this other one. This looks like a pretty useful test. Again, this is in Stefano's cell documentation, his tutorial, which I thought was pretty neat, and we could just observe this as we go through it. To begin with, there's also one thing to be aware of. One is there are two ways cells can be lazy. To reiterate what they are. Technically, once asked is immediately after creation, don't do anything, okay? And don't respond to any dependencies, okay? Another one is don't evaluate immediately after creation itself. Okay, don't evaluate after instantiation. Okay, we saw that earlier when we did C question mark once. Okay, on the family. That's a particular thing to be useful just mainly because sometimes you don't necessarily need the initial evaluation to occur at construction time. An example of that is probably when you're reading in, say, configuration and trying to set up state, and you're trying to make sure in a particular model that a certain value actually changes. Well, of course, it's going to change the first time you actually construct the object. It was just constructed, right? So you don't you may want to suppress that that change event from being handled, and wait until the first actual change event to occur. So sometimes you may end up having to create models that look like this. Okay. One way to actually go in and define this is using. We tried to use the ruled cell macro that was provided, but it looked like that there were some issues there when we do until asked. Another way of doing it is actually explicitly calling out those keyword variables, because when you if you actually macro expand this guy, sorry, not this guy, macro expand this guy, this C dependent is actually creating some rules related to the value state and unevaluated sections, okay? And you can actually go in and convert that to using, to explicitly call out these cells by using something called C formula, all right? And then you can call out when the evaluation actually occurs, all right? So we're going to do a lazy cell example here. This is going to be our slots. And this, again, the reference of this is also a good old, I think I actually have it somewhere here, github.com, this guy. Okay. There he is. Okay. And this one has three kinds of slots that we can actually go and access. Obviously, we're going to go ahead and set this up to being lazy1, just so that we're calling it without a lack of a better term. The init form is going to be cells C-formula, okay? And now C-formula, if you look at this, you have certain keys that it could take in, and then whether or not it's a lazy cell or not, okay? So what we're going to do is we're going to say that our first cell is going to be lazy once asked, okay? And again, this means that upon initialization, upon construction, we'll evaluate this rule, but it won't be reevaluated immediately when change events occur, only when they are read. Okay, so you will end up having some issues there. Okay, if you're trying to assume that those change events are happening in real time. All right, well, concurrently whenever a change event actually occurs. So in this first example, we're going to go ahead and we're going to just simply let's do this. Let's actually create an input cell here. Val init arg is going to be val, so we could pass that into thing, and our form. You need to provide like a like any cell an init form to actually provide the rule, and this init form is going to be cells and :c in, and we're going to set it to nil. Okay, so that's our input cell. Then here, what we're going to do is we're just going to append val on cell self, okay, with an additional list, and we're going to go ahead and put two things here. Okay. So now we have our first lazy cell. The second one is going to be lazy2. And obviously I could make these into readers because these are all ruled cells, but for the time being, I'm not doing that. If you have these as, what's their word? Has accessors, and they're ruled cells, they will call explicit change events on themselves, but anytime their rule gets triggered, it's an unstable state and will recompute the actual cell itself. So beware when you do that setf. Because it's just like your spreadsheet program. So in this example here, we're going to call init form, and let's do until ask here. So let's see if these actually still have it. So there's another one that they question. Yeah, there is one. So we can use this, which is another notation for until ask, and do val self, self. Okay. And then lazy3, and you can also define this as until ask as well, but there's a difference between the lazy3, which is lazy3 is always, and that's going to be noted by this guy here. Okay, and if we do that, we're going to go ahead and do a reverse on the list. Okay, val cells self. Okay. Now, one thing to be aware of is you could certainly label this like we did with cell formula and say, and I'm going to show you this with the same example with two additional ones. So lazy2 is going to be the same as lazy4, because what we're going to do is we're going to use the cell's formula, call this guy lazy, and say until ask. Okay, and then this guy is going to be exactly the same value as cells. So, and lazy 5 obviously is going to be the same as form here. Let's see here. This is going to be cells, the formula, lazy, always. And then we're going to have reverse. Okay. Okay. So now we have this this lazy model. Okay. And what we'll do is we're going to attach a couple of observers too as well, so you understand the difference on when these are actually being evaluated. Okay. Def cells observer. Oops, sorry. Def observer. I'm just going to put these on lazy 1, 2, and 3 just because the other 2, as I said, is just another syntax for actually defining your lazy evaluation. Okay. So here again, we need to define what self is, and our self is our lazy cell example. And we already know what this is going to be, so we're just going to go ahead and, since we're just going to go ahead and print evaluating lazy 1. It might be better just to be format T here, just to make sure that I can get this string here. And I'm just going to go ahead and copy this and make 2 more. This. There. 3, 3, 2. Okay. So now we're going to go ahead and do we're going to go ahead and define a quick function that's going to essentially evaluate these guys into when we call them out. Okay, and it's very important to be able to do this. Obviously, I'm just kind of making it so that we can actually print this guy out later on. Going to take an object, then format T, printing values, format T1, interesting. Can't even find that. That kind of sucks. I don't know why you did that. 2, 2, 3, 3. Okay. So now we have our printing function, and we're going to go ahead and write a very quick function to test this all out, okay? To try it out. Try lazy example. And this guy is going to create a let. Create a quick instance of our lazy cell example with the value of being the cells cn. I'm very lazy. Okay. This is just a quoted list. As you remember, this is a quote with atoms. So I'm very lazy are all atoms right now. So expect them to be capitalized for folks who are looking at this. Now we're just going to go ahead and say format t initialization finished, because we just constructed the actual in the start of the let block. Now we're just going to go ahead and call print lazy on L, and then let's go ahead and change the evaluation of the list that we just provided. So format t changing the val of lazy cell example instance. And what this is going to be is grabbing our list that we provided the bat earlier and changing it to who will be evaluated, right? Nothing special about this, but it's going to illustrate the functions. Okay. What is the warning? Oh, this. Okay. So now, let's go ahead and run. Try lazy example. Okay. And you're going to see here that the first time we encountered it, during construction, lazy1 is automatically called, okay? Before initialization is completed, okay? So lazy1 is, the first time it changed, it actually goes ahead and calls it, okay? Now, when you're printing values, though, you are lazy1 is going to go ahead and get printed out because it's already been evaluated, okay? But lazy2 is first evaluated because it's until asked. We just asked for it, so it's evaluating it, and it's not going to do it, okay? Same thing with lazy3, okay? Which is particularly interesting, okay? And to really show, I think I have to add one more. I'm going to probably have to add the other two. Let me go ahead and add the other two. Oh, dang it. There. Okay. And let's go ahead and add okay. Go ahead and bust this guy out, bust this guy out, bust this guy out. And now we're going to actually see a different output. Okay. So since we asked for Ooh, that's probably a better way of doing it. Let me change the ordering of this guy. Okay, so let's look at this here. Okay, so the first time again we said that lazy one once asked, so construction occurred, it's going to immediately get um, uh, changed. It's going to go ahead and evaluate. Right. Second time here, as you can see here, lazy 5 is lazy 3. And again, I said that the other it's just a shortcut versus the actual macro expansion using C formula. What this is doing is it's going to go ahead and just reverse the list. Okay, but notice before it prints out, it's first evaluating it. So 4 and 5 are going to act very, very similarly. All right, because of the fact that until asked and one always, very slight difference in terms of their behavior. Okay, again, always basically means until read, don't do the initial evaluation, and even after a change event occurs, do not reevaluate until the next read. All right. So every time a change event occurs, a read is not. Lazy 4 and lazy 5 have the same exact behavior. They're not going to evaluate. All right. They're both very lazy. All right. It's just that always is lazier than until asked, obviously. So those guys are going to be postponed. And then you can see here that evaluating 2 is until asked, okay, which is the same as lazy 4. And you can see that 2 and 4 are going to do the exact same behavior, all right? And then obviously with 1, we've already evaluated. We don't have nothing to worry about. So what happens when we're changing the value of the instance, though? Well, here's where things get a little bit interesting. 4 gets evaluated first, then 2. Well, why? Because of the fact that 4 and 2 are until asked. Okay, they're not always. They're until asked. Okay, so and until asked, if you look at the documentation on until asked, it's going to eagerly evaluate every time a change event occurs. It won't eagerly evaluate when the object is constructed, but it'll eagerly evaluate when a change event occurs. Okay, so that means the first time those values get changed, these guys are immediately going to go ahead and evaluate. Okay, subtle difference from once asked. Once asked basically is saying at construction time I'm going to be eager, and then after that I'm going to be lazy. Until asked is at construction time, object construction time, I'm going to be lazy, but every time a change occurs, I'm going to make sure that everything gets evaluated properly. Always is, regardless of construction or change events happening, unless somebody's asking for it, I am not going to do my work. So that's the epitome of laziness, all right? So you make sure that your particular use case requires those things. So lazy 4 and 5 here, 4 and 2 are going to behave differently. And then obviously when we're printing the values, we printed 5 first. Okay, then that means we're going to, that's always, so it's going to evaluate. 4 has already been eagerly evaluated, so it's not going to be evaluated. 3, again, is the macro version of the C formula that I wrote out, so it's going to be evaluated. 2 is not going to be evaluated. And finally, 1, because it's once asked, okay, it's going to be evaluated. It's the opposite of until asked, okay? Just remember that. your laziness use cases will determine whether or not you're going to be once, until, or always. Sometimes you want to hold off until an actual change event occurs. All right, which means you'd want to do once asked and then be lazy every time. Okay, so set up the initial state, keep going. But sometimes you want to be eager and always keep your entire system up to date. All right, but you don't need to know about its initial change occurring when it was first constructed, in which case you'd want to use until asked. And if you just don't care, I'll do the work when you ask me to it. If that's your policy for your application use case, then you want to use always. Okay? Does this make sense for folks? Okay, I'm assuming the single letter confirmation from our audience means that we are good. Let's check the folks watching right now. Okay. All right. I think with that, I am going to go ahead and stop for today. Just because there's a few more topics on the cells library that I really want us to dig into. One is a topic of drifters, which is a concept in the cells library, just to give you kind of a taste of what's going to happen next week. It's a specific type of cell, which is a ruled, and specifically the type of ruled cell, but how the body of the rule is interpreted is slightly different than a normal ruled cell. And then we're going to also touch base on a concept of the concept of cyclic dependencies in your models, as well as a actual topic which closes out this library evaluation on synapses and how to handle synapses, which is a concept of designing synapse, like essentially reactive networks. Okay, at least that's how I understood it. So next time we'll cover drifters, cyclic dependencies, and synapses, and I'll give you kind of like an overview of probably come up with an example of an application that we can cover to like really tie all these things together. So until next time, I appreciate all of you guys staying with us, and I'll see you guys next week. One final thing before I let you guys go. Tomorrow, just a reminder, we will be covering lists for the Haskell study group. That's the chapter on lists in Learn You Haskell. If I remember, may as well just pull it up. It's going to be, for folks following Learn You Haskell, it's going to be, where is it? Not modules, not inputs and outputs. I think it's going to be covered in various forms inside interesting. I don't think there's a specific section on lists and how to handle lists inside of Learn You Haskell. Outside of maybe Chapter 2, covering it a little bit. Chapter 7 touches it a little bit, specifically the section on data.list. That's essentially what we're going to be covering. And for folks who are obviously reading the Haskell book with us, the chapter that we'll be covering is Chapter 9. So folks following Chapter 9 in Haskell book or Chapter 7 in Learn You Haskell, we'll be covering lists tomorrow. I hope you can join us. Same time, 1:30 to 3:30 p.m. Eastern Time. Please adjust it to your time schedule in your own time zone. And I'll see you guys tomorrow. For folks who are joining us in the Haskell study group, Otherwise, I'll see all of our Lispers next week when we cover the final pieces of cells.